Hello, and welcome back to Greg Does Physics. My name is Greg, and we're going to be doing some physics. So we are going to be doing problem 1.17 from Griffiths E&M. The problem asks, in two dimensions, show that the divergence transforms as a scalar under rotations. Hint, use equation 29 to determine Vy bar and Vz bar, and the method of problem 14 to calculate the derivatives. Your aim is to show that dvy bar, dy bar plus dvz bar, dz bar equals dvy dy plus dvz dz. Now that hint, the last part of it isn't especially clear about why that is what we're looking for. And the reason is because, well, let's take a look at the equation for the divergence. The divergence of a vector v is just the dot product of the del operator dotted with said vector v. And in two dimensions, our two dimensions are y and z. It would be this equation, dvy dy plus dvz dz. Now, if we were to re-express this in a new coordinate system, specifically under a rotation, as the problem asks, it asks us to show that the divergence transforms as a scalar under rotations. And so this is the same rotation that's used in the section earlier in the book, How Vectors Transform, that sort of goes into detail about what it means to be a vector, and then also introduces the concept of tensors, scalars, things like that. And in the example, it uses this idea of a rotation about some common axis. We can say it's like an x bar axis pointing into or out of the board. And again, in problem 1.14, which is sort of a predecessor to this because it's asking you to do a very similar thing, except rather than showing, in this case, we're showing that the divergence looks like a scalar under rotations. It asks you to show that the gradient of a scalar looks like a vector under rotations. And so a rotation in this case is, we can imagine taking our coordinate system yz and rotating it by a given angle phi. And so before I get too much further into this, I want to just talk a little about what we're looking for, what it means to be a scalar versus a vector, because in the 1.14 we showed that it was a vector and not a scalar. And Griffiths kind of gives a crude definition for vector. He says that you can imagine a vector to be something that transforms in the same way as a displacement under some change of coordinate system, like, for example, a rotation. A scalar would not transform in this way. A scalar would be the same before and after this transformation. And I think if you think a little bit about this, this might be a little bit confusing, because you could imagine if a scalar has some dependence on location, for example, you have some equation for, let's say, temperature in some three-dimensional space. If you change your coordinate system, then that equation is going to change. But that's not really what we're saying here. We should be thinking about it more as the value of a scalar at a certain point. Or likewise, in the case of a vector, the value of a vector at a certain point. How do these things change under a given change of coordinate system, change of basis? If I say that, say, this spot in the room has a temperature of 72 degrees Fahrenheit, whether I put the origin over there or there, if I rotate my coordinate system, this spot is always going to be measured to have a temperature of 72 degrees Fahrenheit, regardless of the coordinate system I'm using. Now, on the other hand, if I had a vector, say that I was pointing from some point say in the YZ system, I had a vector that looked like this, and we'll give it an equation of, I don't know, maybe y hat plus 2 z hat. And then we re-expressed this vector, we want to re-express this vector in the y bar, z bar, this rotated coordinate system. If we said y hat plus 2 z hat, or I guess in this case it'd be y bar hat plus 2 z bar hat, that wouldn't give us this vector. That would give us something more over here, I guess, which is obviously not the same vector. So this vector would have different coordinates, a sort of different label or name for it in the new coordinate system, and that's sort of the subtlety behind the difference between a scalar and a vector. You can say that a vector has a direction and a magnitude, a scalar just has a magnitude, and including that direction is sort of what creates this need to re-express something in a new coordinate system. Because while the magnitude of this vector will be the same in both coordinate systems, just like the magnitude of a scalar will be the same in both coordinate systems, the direction it has with respect to that coordinate system does change once you change the coordinate system. A scalar doesn't have that same problem. One last thing I want to talk about, just to sort of clarify a point I made in an earlier video, is that I mentioned that vectors do not have a location. Griffiths also talks about this in his textbook, but I want to say that that is true, but I think it could be easy to get confused, like with my prior example with the scalar, of how something could have a location dependence. You know, you could create an equation for some scalar or some vector that changes with location. For example, once you get into electrostatics, Coulomb's law will give us kind of like the simplest form of expressing the electric field, which is a vector field, given a certain charge distribution. But that equation, that idea, does have a dependence on location, on R. And so when I say, or when Griffiths says that a vector does not have a location, he's not saying that a vector cannot have a dependence on being placed in some point. But what he's saying is that if you have a vector that, say, the vector I've erased now, y hat plus 2 z hat, whether I place that vector here or here or here or here, anywhere, that vector is still going to be given by the same label, the same equation, that the same coordinates, the y hat plus 2 z hat, regardless of where you place it. And that's sort of the distinction there, is that I can place that vector in different places, but it will still have the same label. In the same way that saying the temperature here is 72 degrees, you're still expressing it in the same way. The temperature is 72 degrees. So that is a long sort of preamble, just to sort of go into a little depth about the distinction between a scalar and a vector and some of the underlying ideas behind these concepts. But I want to go ahead and get into the problem, so that this isn't a half-hour-long video for a problem that doesn't take a half hour to do. So I'll return back to this. Griffiths said that we want to show this equality right here. And the reason being is because if we change our coordinate system, our vector v, since the vector v is going to be expressed in a different way in the new coordinate system. So that's why we have vy bar, vz bar. But likewise, the displacement, the y and the z, also are changed under the new coordinate system, so we have to have the bars there. This is subtly different to problem 1.14, where this was not what we were looking at. We were looking at the derivative of a scalar, f, with respect to some coordinate, x bar, y bar, or whatever. And so that's totally different because, as I've said a couple times now, a scalar does not change under a coordinate system like a displacement or like a vector. And so we didn't have to spend extra time transforming that scalar f. But since what we're doing is we're taking the partials of vector components, the vector does change, and thus its components will change. And so to get this equation for the divergence of the newly expressed vector in the newly expressed coordinate system, we have to transform both of them into the new coordinate system. And then once we show that the divergence as calculated in the new coordinate system is equal to the divergence as calculated in the old coordinate system, only then can we say clearly the divergence is the same before and after this transformation. Ergo, we can say that the divergence is a scalar. So the hint also pushed us to look at equation 1.29. That is this sort of matrix equation here. I won't go into depth on how this how you calculate this. It's just geometry. You can see how it's calculated if you want to read the section in the textbook on how vectors transform. It shows how this is derived. But basically it's just saying that a component, the y component in the newly rotated system of some given vector is equal to cosine phi times the old y component of that vector plus sine of phi times the z component of the old vector, or the vector how it was expressed in the prior coordinate system. And so that's basically just what that's saying. We're going to use this so that we can transform our Vy and our Vz, this actual vector, into the new coordinate system, since we know that it'll take this form. And then I'm also going to here reference a result that we got from problem 1.14. You can calculate these yourself, or go back to my video on problem 1.14 and I derive these, but so as not to sort of do the same thing over again, I just wrote these results out here. So let's get into this. How do we show this? So it asks us to use a method of derivatives similar to what we did in problem 1.14. So if we were to look at this term on the left here, d vy bar dy bar, what would this method of derivatives be? And it's just it's basically just using our partial derivatives like you would learn in a multivariable calculus, like introductory course. So d vy bar dy bar plus d vy dz. So it looks something like this. But we also know that our Vy bar equals, using this equation here, Vy cosine phi plus Vz sine phi. And likewise, Vz bar expressed in the new basis is minus Vy sine phi plus Vz cosine phi. Okay? And then we can write out basically the same equation for dv z bar dz bar, and then we would add those two. So, well, I'll just write this out further. So this would be d dy times this equation. So d vy dy cosine phi plus d vz dy sine phi. So that's this first term here, and that's multiplied by dy bar, which we are saying is cosine phi. Again, look at the video for 1.14 or do 1.14 if you're curious how we got these values. And then d vy bar derived with respect to z. So d vy dz cosine phi plus d vz dz sine phi, and then multiplied by dz dy bar sine phi. Okay, so likewise dvz bar dz bar would equal dvz bar dy. So that'll be minus dvy dy sine phi plus dvz dy cosine phi, and then it would be multiplied by dy bar. Oh no. Dy dz bar, excuse me, which is minus sine of phi times minus sine. I'm just gonna put the negative into here. Sine of phi, right? Because that's y z bar. Okay. Plus, and then over here we would be looking at dvz bar dz. Dz sine of phi plus dvz dz cosine phi, and then it would be dz bar is cosine phi. And so then finally, what we want to do now that we have these two is we want to add them up. So dvy dy bar plus dvz bar dz bar equals, and we'll do this by partial terms. So dvy dy is cosine phi, or excuse me, cosine squared phi, because it's cosine. And then do we have another dvy? Yeah, and so then down here we have a sine squared term. Then plus dvz dy is sine cosine. Okay, and then dvz, and then this is minus sine phi cosine phi, and then plus dvy dz, and this is cosine times sine, and then down here dvy dz minus sine times cosine, and then our last term dvz dz, which over here is sine squared, and then down here is cosine squared. These two, of course, equal 0, these two, of course, equal 0. And then sine squared plus cosine squared is 1. And so thus, this all works out to dvy dy plus dvz dz. And there we go. So dvy bar dy bar plus dvz bar dz bar equals dvy dy plus dvz dz. This is the result we're looking for. And dot 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 QED, we've shown that under a rotation in 2 dimensions from about an angle z around some common x equals x bar axis, we have shown that the divergence for a given vector v is the same whether you calculate it in the old coordinate system, the old basis, or the newly rotated basis. And thus, since it's the same before and after, then it must be a scalar. And that's all. Thank you for watching.